Hello friends, in the previous lecture we have seen that what is meant by relation and reflex relation. Today we are going to start second type of relation is symmetric relation. Okay, so what do you mean by symmetric relation? Okay, second definition is symmetric relation. Okay, so write down definition. What do you mean by symmetric relation? A relation capital R on set X. A relation capital R on set X is said to be symmetric. Relation is said to be symmetric relation on X if whenever X comma Y belongs in R. If X comma Y belongs in R, then Y comma X also belongs in R. Then R is symmetric relation. What is symmetric relation? A relation R on set X is said to be symmetric relation if X comma Y belongs in R, then YX is also belongs in R, then R is symmetric relation. That is a relation R on X is symmetric relation. A relation R on X is symmetric relation if X is related to Y. If X is related to Y, then if X comma Y belongs in R, that means X is related to Y, then Y also belongs in R. That means then Y is related to X, then R is symmetric relation. Okay, let's take example. Let capital X be set of all lines. Let capital X be set of all lines in a plane. Okay, your set X is set of all lines in a plane, and define a relation R, on X is, we will define relation R on X is, let X comma Y, the small x small y, be elements of that set capital X comma Y belongs in R, that is X related to Y. If we have to define relation X comma Y belongs in R, what is your relation defined? X Y belongs in R if X is perpendicular to, if X is perpendicular to Y. What is your relation? We have to define relation X related to Y is X is perpendicular to Y, then R is symmetric relation. Why is it symmetric relation? Interested? What is the symmetric relation? If X, Y is related to R, then YX also belongs in R, then R is symmetric relation. So let X comma Y belongs in R. Right? What is given? X comma Y belongs in R. That means X is perpendicular to Y. That means X is perpendicular to y. That is, the line x is perpendicular to y. That is, suppose this is your line x, this is your line x, this is your line y. Okay, line x is perpendicular to line y. Then this is your relation. Also, this line y, this line y is also perpendicular to line x, right? Therefore, also line y is perpendicular to line y is perpendicular to x also. This line y is perpendicular to x also, right? Then y comma x is also element of R, right? What is relation? That is perpendicular line. Y is perpendicular to x, that means y comma x is belongs in R. Therefore, R is symmetric relation, right? Therefore, R is symmetric relation. Let's take the third type of relation is transitive relation. What is your third type? That is your transitive relation. Okay? Let us take third type. It is showing the definition. Third definition is transitive relation. What do you mean by transitive relation? Let us write down definition. A relation capital R on a set X. A relation capital R on a set X is said to be transitive relation. A relation R on set X is said to be transitive relation if x comma y and y comma z is a member of R. If x, y and y, z is a member of R, then x comma z is also member of R. That is, first is related to y, that is first related to second, and second related to third, that is y related to z. Then x related to z, that is first related to third. Then this relation is said to be transitive relation. That means, and here x and y is member of capital X, right? There is x, y and also z. Okay? All these three members are your set capital X, that non-empty set, right? All these members from X, right? That is, what is my transitive relation? That is a relation R on set X is said to be, a relation R on X is said to be transitive relation, is said to be transitive relation if whenever x, y belongs in R, that is x related to y, whenever x related to y and y is related to z, then x is related to z, then this R is transitive relation. Okay? What is my transitive relation? If x is related to y and y is related to z, then x is related to z, that means your R is transitive relation. Okay? Let us take example of transitive relation. Let capital X be family of members. Let capital X be family of members and define a relation R, and define a relation R on a set X is, we will define a relation R on set X is XY belongs in R if, we will define a relation R on set X is X, Y belongs in R. What do we mean by that? XY belongs in R means X is related to Y, right? X is related to Y if this possible, if X is brother of Y. What is your relation defined? When this X is related to Y, if X is brother of Y, then this XY is member of R. This is your relation. Okay? Then R is transitive relation. R is transitive relation. Why is it transitive relation? Understand? Why is it transitive relation? What is the transitive relation? If X is related to Y and Y related to X, then X is related to Z. Then this R is transitive relation. Let XY belongs in R, right? It is also X is related to Y. When is X related to Y? That means X is brother of Y, right? That implies X is brother of Y, right? And also, what is the second condition? Y related to Z. That is Y comma Z belongs in R. That means Y related to Z means Y is brother of Z, right? So what do we get? If X is brother of Y and Y is brother of Z, then we know the family relation. If X is brother of Y and Y is brother of Z, then X is obviously brother of Z, right? Then X is also brother of Z also, by family relation. X is brother of Z. X is brother of Z, that means X comma Z belongs in R. And if X comma Z belongs in R, that means R is transitive relation, right? This is your example, right? So let's take the next definition. What is meant by equivalence relation? Okay. So next definition is, what is meant by equivalence relation? Next definition is, definition of equivalence relation. What is meant by equivalence relation? Okay. Write down definition. Let capital X be any non-empty set. Let capital X be any non-empty set a relation capital R on a set X. A relation R on a set X is said to be, a relation R on set X is said to be equivalence relation, is said to be equivalence relation if R is reflexive, symmetric, if R is reflexive, symmetric and transitive relation. If R is reflexive, symmetric and transitive relation, then this R is said to be equivalence relation. Okay? What is my equivalence relation? A relation R on set X is said to be equivalence relation if that relation R is reflexive, second one symmetric, and third one transitive. If R satisfies all these three conditions, then this R is said to be equivalence relation. That is first case. What is the reflexive? Let X is a member of capital X such that X comma X belongs in R. X comma X belongs in R. Then this R is reflexive. Right? What is the second case? R is symmetric. That means let X comma Y is a member of capital X such that implies if XY is a member of R, then YX is also member of R. Then R is symmetric relation. What is your last third one? Transitive relation means let X comma Y comma Z. Let X comma Y comma Z be element of your set capital X such that if X comma Y is member of R and Y comma Z is also member of R, then if XY and YZ is member of R, then X comma Z is member of R, then R is equivalence relation, right? Then R is equivalence relation. Okay? So if R is equivalence relation, then it is denoted as. So the next remark, it is denoted as symbol. Which symbol? That equivalence symbol. What is meant by this symbol? This equivalence symbol is used for equivalence relation. It is denoted as symbol that equivalence, right? For equivalence relation. Okay? Now let us take the example. Okay? So let us take example for equivalence relation. Right? Let capital X be set of all lines. Let capital X be a set of all lines in a plane. Okay? Let capital X be a set of all lines in a plane. Define a relation R. Define a relation R on a set X is. Define a relation R on a set X is. Let X and Y is member of S. That implies X comma Y belongs in R. We have defined X is related to Y if X is parallel to Y. If line X is parallel to Y, then show that R is equivalence relation. Then show that R is equivalence relation. Okay? What is your equation? X is set of all lines in a plane. That is this is your plane. Your blackboard is your plane. So X is set of all lines in the plane. we have to define relation R on set X is X comma Y belongs in R, that means X is related to Y if X is parallel to Y. If line X is parallel to line Y, then this X is related to Y. Okay, we have to show that this relation is equivalence relation. So write down solution. What do you mean by equivalence relation? Equivalence relation means it is a reflexive, symmetric and transitive, right? So write down first condition is to check that it is reflexive, right? And your question is show that, then you have to show that it satisfies reflexive, symmetric and transitive relation. Okay. So what is your first reflexive? Let X belongs in capital X such that X comma X belongs in R, such that X comma X belongs in R. That implies X is parallel to X also, right? That means suppose this is your line X, okay? This is your line X. This line X is also parallel to itself line, right? This line X is also parallel to itself line. Therefore, X is parallel to X. That means X comma X is related to R. X comma X is related to R. Therefore, R is reflexive relation. What is the first property? The second property. Symmetric relation. What is the second property? Symmetric relation. So what do you mean by symmetric relation? Let X comma Y be member of capital X. That means your X and Y are two lines in a plane. Okay? Such that X comma Y is a member of R. That means X is parallel to Y line, right? That means this is your line X, right? If this line X is parallel to line Y, right? So that means this line Y is also parallel to line X, right? That implies Y is also parallel to X, right? Now Y is parallel to X, that means Y comma X is also a member of R. That means Y comma X is related to X. That means what is your answer? X comma Y is related to R. So we get Y comma X related to R. That means your second condition is whole. Therefore, R is symmetric, right? Therefore, R is symmetric. Okay? Now we have to show that last third property. This R is transitive, right? But on the last one, third property, we have to show that R is transitive. Third property is transitive relation. We have to show that R is transitive relation. How to show that? Let X comma Y comma Z be three lines in a plane such that X comma Y is a member of R, right? That means X is parallel to Y, okay? And what is given? Y comma Z also is member of R, right? Now Y comma Z is member of R, that means Y is parallel to Z. How this comes, these two statements? Because we have given defined a relation. X is related to Y, that means X is parallel to Y. Similarly, Y comma Z is related to R, that means Y is parallel to Z, right? This is also defined relation, right? That means if this line x, right, this line x is parallel to line y, right. Also we know y is parallel to z. This line y is parallel to line, this line y is parallel to line z. That means this first line is also parallel to last line, third z line. This line x also parallel to line z. That implies x is also parallel to z, right? That implies x comma z belongs in R. That implies x comma z belongs in R. That means R is transitive relation. That means R is transitive relation. Therefore, so what do you get? So your R is reflexive, symmetric, and transitive. So we get R is reflexive, symmetric. R is reflexive, symmetric, and transitive relation. Therefore, R is equivalence relation, right? Therefore, R is equivalence relation. It is so easy. If we are given any example, for that show that R is equivalence relation, that means we have to show that R is reflexive, symmetric, and transitive relation. Okay. This is for example parallel to Y. Okay. We can check also if x is set of all lines. This is your second example. If x is set of all lines in a plane, and we will define a relation R on a set x, that is x comma y related to R. If x is perpendicular to y, if x is perpendicular to y, that means line x perpendicular to y. This is your relation, and we have to check that this R is equivalence relation. So for this condition, I am checking that orally. So we have given x is set of all lines, right? If x is set of all lines in the plane, and your relation R is x is perpendicular to y, then this x comma y belongs in R. So for the first condition for reflexive, and this relation R is not equivalence relation. Why this relation is not equivalence relation? For we have to first check that is reflexive. So for reflexive, if x is lying on x such that x comma x is member of R, right? That means x is perpendicular to x, right? That means if suppose this is line x in your plane, and what is this gives that x is perpendicular to x. That means this line x is it perpendicular to itself? This line x is perpendicular to itself? No, this is not perpendicular. This line x is parallel to itself. This line is not perpendicular to itself. Therefore, R is not reflexive. Therefore, R is not reflexive. Therefore, R is not equivalence relation. Therefore, R is not equivalence relation. What if R is not reflexive? Then don't check symmetric and transitive condition. Okay? So directly you can say that R is not equivalence relation. Okay? I hope you have understood this all these parts of today's lecture. So remaining part we will do in next lecture. Okay? Thank you.